Okay, good afternoon to all, and welcome to the another session of the NPTEL course Heat Transfer. So today is our week 12 session, and today we will be discussing about the uh, week topics related to the week 12. So the main let's have a brief recap of what are the topics that were covered in the week 12 session. So it was a radiation. It was a continuation of the topic radiation. So in this week 12, so the radiation networks and the radiation shields were discussed. And these are problems related to radiation network exchange and heat transfer exchange, radiative heat transfer between two surfaces or two or three surfaces which are in which will be interacting each other. So using radiation networks and we discussed, and the questions related to that also was so. And also an important concept known as radiation shield, which is used to which is a uh, which is used to reduce the radiative heat transfer between the surfaces. So today we will be discussing some of the questions related to uh, these topics. So let's get started with the first question. So we have a spherical tank of diameter 2 meter is filled with a liquid nitrogen at 100 Kelvin, is kept in an evacuated cubic enclosure whose sides are 3 meter long. The emissivities of the spherical tank and the enclosure are zero point 0.1 and zero point 0.8 respectively. If the temperature of the cubic enclosure is measured to be 240 Kelvin, determine the net rate of radiative heat transfer to the liquid nitrogen. Okay, so we have a spherical tank which is filled with liquid nitrogen, and also we have a uh, cubic enclosure, cubic enclosure into which this spherical tank is fixed. So the diameter of the spherical tank is given as 2 meters, and the liquid nitrogen. So this is the spherical tank we are talking about. So its diameter is 2 meters, and the temperature of this tank is 100 Kelvin. And this is evacuated, which means that only the between this spherical tank and this cubic enclosure, the mode of heat transfer is radiation. So the convection and all is arrested. So the sides of the cubic enclosure is given as 3 meter, and the emissivity is I'm taking this surface, that is spherical surface as 1 and cubic surface as 2. One is a sphere and surface 2, I am naming it as the cubic enclosure. Okay. So So we are asked to find out what is the net heat radiative heat transfer between these two surfaces. This cubic surface is maintained at 240 Kelvin. So and the emissivities, that is epsilon 1 and epsilon 2 of the uh, cubic spherical tank and cubic enclosures are given respectively. So let us draw the radiation network. So this is EB1, that is heat is getting means transferred between the spherical surface spherical tank and the radiation sorry, the cubic enclosure. So we have the EB1, and also we have the it's not a black body, so it has some resistance. That is EB1A1. This is J1, and then we have the phase resistance, that is 1 by A1 F1 to 2. Then again we have this resistance, so and EB2. So this is the surface resistance. Okay. So this is the radiation network for our case. So the Q net is equal to EB1 minus EB2 whole divided by the total resistance. That is 1 minus epsilon 1 by epsilon 1 A1 plus 1 by A1 F12 plus 1 minus epsilon 2 divided by epsilon 2 A2. So we will evaluate each term, that is 1 minus epsilon 1 by epsilon 1 A1. Epsilon 1 is given as 0.1. It is 1 minus 0.1 divided by 0.1 into A1 is 4 pi r square. So the diameter is 2 meters, so radius is 1 meter, so 1 square. So this will come out to be around 0.716, and this is 1 by A1 F12. This is F12 will be 1 because I already explained the previous sessions also. Means the sphere, whatever the radiation that is emitting from the sphere, it will be, as it is completely enclosed in the cubic structure, it will be completely absorbed or reaching to the cubic enclosure. So none of the part is reaching back or reaching directly to the spherical surface. So it is because of the uh, means this geometry of the sphere. So this is one. Okay. So that is 1 by 4 pi into 1 square into 1, which is equal to 0.08. And we have 1 minus epsilon 2 divided by epsilon 2 A2. So epsilon 2 is 0.8 into, so the cubic, what is the surface area of the cube, that is 6 a cube, right? That is 3, it is given us 3 meter long, 3 square, so which is equal to 0.46. So the Q net is, it will be calculated as 5.67 into 10 raised to minus 8 100 raised to 4 minus 2 40 raised to 4 all divided by 0.716 plus 0.008 plus 0.0046. So the answer will come out to be minus 227.81. So which means that, so this I am calculating the Q1 to 2. That is, so the minus, it is showing that actually the heat, the sphere is, the heat is getting lost by the sphere. That is what the negative, that is, sorry, the heat is getting gained by the sphere. This will be positive. Okay. So I hope this was clear. This will be. So heat is not getting transferred from 1 to 2, but opposite is happening. That is, the heat is getting transferred from 2 to 1, right? That is why the negative has happened. So heat transfer takes place from, not from 1 to 2, but this is what we assume. Like initially we assume that it is taking from 1 to 2, but not actually, the opposite is happening, because obvious, because of the temperature of the cube is small, the cubic enclosure is small. So heat is getting transferred from the cube to the sphere, or the sphere is gaining. Okay, let's move on to the next question. We have a thin aluminum sheet with an emissivity of 0.15. On both sides is placed between two very large peroxides, which are maintained at uniform temperatures of 900 Kelvin and 650 Kelvin uh, respectively, and has emissivity is also given. Determine the net rate of radiation heat exchange between the two plates. That is what we need to find out. Okay, so so I think so we have two aluminum plates. Sorry, two parallel plates. We have. So the emissivity is given. I am taking this as 1 and this as 2. So emissivity is zero point 0.5 and temperature is 900 Kelvin. This is E2, that is zero point 0.8, and T2 is around 650 Kelvin. So in between, we have a thin aluminum sheet which is placed. So its both side has, I'm naming it as 3. Its both side has the emissivity of 0.15. Okay. Uh, we have to find out what is the net heat radiation heat exchange between 1 and 2. Okay. This is what we need to find out. So just we will just we can draw the radiation network. Mhm. Yeah, J1. This is the surface resistance of so of this. Then we have the space resistance. Surface resistance of the first plate. Then space resistance. Then we have the surface resistance of this shield on the left side. Then we have the surface resistance of shield on the right side. Then we have the space resistance from shield to this to the or from 3 to 2. Then we have the space resistance of the sheet other sheet too. So these are the total resistance. So if you first calculate the total resistance. So as the air, it's a parallel plate, we will be calculating in flux. So uh, so all these areas will be equal and we can take it outside. Okay. So so we will be calculating it the net flux. So the area all are same and as it is as we are taking the flux, we will take areas outside. So we will take 1 minus epsilon 1 by epsilon 1 plus 1 by F13 plus 1 by epsilon 3 divided by epsilon 3 by epsilon 3 plus 1 by F32 plus 1 minus epsilon 2 divided by epsilon. And this F13 will be equal to F32 will be equal to 1 because these are parallel plates. So whatever the radiation that is emitting from one surface, it should reach the nearest surface. Okay. So these all are same. So we will simplify it as So this cancels, this cancels, and 1 by epsilon 1 by plus 2 times. So this is the simplified equation for the simplified resistance. So now just we need to substitute the values. We will get the answer, that is Q net Q1 to 2, that is Q net is equal to EB1 minus EB2 divided by 1 by epsilon 1 plus 1 by epsilon 2 plus 2 times 1 by epsilon 3 minus 1, which is equal to 5.67 into 10 raised to minus 8 into 900 minus 900 raised to 4 minus 650 raised to 4, all divided by 1 by 0.5 plus 1 by 0.8 plus 2 times 1 minus 0.15 minus 1. So if we can do the math, you will get the answer as 1857.3 watts per meter square. So the radiated heat flux between 1 and 2 with shield. Okay. So let's calculate what is. So this is question number 3. It's also a continuation of the question number 2. So we need to find out the ratio of the heat transfers with shield and without shield. Okay. So without shield, we just I will draw this 950. So without shield, this is 1 and this is 2. Epsilon 1 is 0.5 and T1 is 900 and T2 is 650 Kelvin. Okay. So let's draw the radiation network. There's a space resistance. So I'm not writing the area factor here because we are calculating the net heat flux. Sorry, heat flux. So if you write the resistance 1 by epsilon 1 minus 1 plus 1 plus F12 will be 1 by epsilon 2 minus 1. So we'll calculate 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So Q without shield this will be equal to EB1 minus EB2 divided by R, which is equal to 5.67 into 10 raised to minus 8. 900 raised to 4 minus 650 raised to 4, all divided by 1 by 0.5 plus 1 by 0.8 minus 1. So you will get the answer as 12035.36 watts per meter square. This is without shield. So we are asked to find out the ratio of with shield to without shield. Q with shield divided by Q without shield. We'll get it as 1 2. Sorry, with shield is we calculated in the previous question, that is 1857.3 divided by 12035.36. So if we calculate, it will be becomes 1 by 6. So you can see the relevance of putting a radiation shield here. So by just putting a radiation shield, our heat transfer of radiation, a single radiation shield of emissivity 0.1, the heat transfer between these two plates got reduced by 1 by 6. Okay. So That is why we are usually putting, that is the importance of putting radiation shield. Okay. Let's move on to the next question, that is the fourth question. So consider a cylindrical furnace with R is equal to H 1 meter. The top surface and the base surface of the furnace has emissivity is given 0.8 and 0.4 respectively, and are maintained at uniform temperatures of 400 Kelvin and 500 Kelvins. The side surface approximates a black body and is maintained at a temperature of 400 Kelvin. And we are given the so here I need to draw the means diagram. This is a cylindrical furnace, and this is the top surface. Uh, top surface I am marking as 1, and the bottom surface I am marking as base bottom surface. I am marking it as 2, and the side I am marking it as 3. These are the sides. Okay. So and its emissivities are also given. So this emissivity is 0.8. This emissive is 0.4, and it is at 700 Kelvin. And this sides is approximates a black body, that is emissivity is 1, and it has 400 Kelvin is the temperature. So we are asked to find the first question. We are asked to find out what the view factors. From first, we need to find out F12, F21, F23, F31. So 21. Okay. So let's write F21 plus F23 should be equal to 1, right? And we are given F12. We are asked to find out F21. Okay. By reciprocity theorem, A1 F12 should be equal to A2 F21, right? So F21 is equal to F12 is given 0.38. So F21 is equal to A1 by A2 times F12. As A1 and A2 are same, that is its cylindrical furnace. So it's a cylindrical furnace. So yeah, F12 is given. So A1 and A2 is same. So A1 and A2 is same. So F21 will be equal to F12, which is equal to 0.38. It's already given. Okay. So next, first view factor is find out, that is F12. Next, we have to find out what is F23. Okay. So from this equation, we can find what is F23 because we already found out F21. So F23 is equal to 1 minus F21, which is equal to 1 minus 0.38, which is equal to 0.62. So the second also we calculated. Next is F31. Okay. What is F31? So for calculating F31, F31 plus F32 plus F33 will be equal to 1. Okay. So but this will be F31 and F32 will be same because of symmetry. Then we can calculate A1 F113 will be equal to A3 F31. So F31 is equal to A1 by A3 F13. Okay. So we need to calculate one F31. So, but we can write the equation for surface one F1 F11 plus F12 plus F13 will be equal to 1. So this F11 will be equal to 0. So F13 we know 1 minus F12. So we already found out F1. It's already given F12. That is we will get 0.62. Now we can easily find out that is A1 is pi r square and A3 is 2 pi r h. So this r is 1. It's already given in the question. So 1 by 2 times F13. So it is 0.31. So all the necessary view factors that are asked where we already found out F21, F23 and F31. Okay. So this is just we already discussed a similar kind of questions in the previous session also. So we just need to calculate the view factors of different surfaces. So the next question is also a continuation to the question number 4, that is the previous question. So we need to determine the radiosity of the surface of surface 1. So just we will draw the radiation network for this question. So we have 3 surfaces, which is starting with first surface. So this surface 1, that is this top surface, is exchanging heat between 3 and 2, both, right? So this is J2 and we have TB2, that is. So this resistance is 1 by A1 F1 to 2, 1 minus epsilon 2 divided by epsilon 2 A2. But this 1 is also interacting with 3, is J3 EB3. Okay. And these 3 and 2 also are interacting with each other. So the radiation network will be something like this, that is A1 F13 and A1 F2 A2 F23, or we can write also as 1 by A3 F32 also, both are same. So but in this question it is given that the surface 3 is black, is a black body. We can approximate as a black body. So there is no surface resistance for this epsilon 3. Sorry, black body 3. So both, so we can, there is no surface resistance. So this is EP3 will be equal to J3 is equal to sigma T3 raised to 4. Okay. So this is our radiation network. So we are asked to find out the value J1, this value. For that, we need to solve a set of equations. So I'm taking this surface. So we know surface 1, that is the surface 1. I'm writing for top surface. For top surface, we have EB1 minus J1 divided by 1 minus epsilon 1 by epsilon 1 A1 should be equal to J1 minus J2 divided by 1 by A1 F13 plus J1 minus J3 divided by 1 by A1 F13. Okay, so I'm just rearranging this. EP1 is equal to J1 plus 1 minus, I'm cancelling the A1 out. This is equation number 1. Similarly, for bottom surface also, we have EB, so IEB2 minus J2, 1 minus EB epsilon 2 minus epsilon 2 A2 is equal to J2 minus J1 divided by 1 by A2 F2 to 1 plus J3 J2 minus J3 divided by 1 by A2 F2 to 3. So the A2 I am taking common. So I'm rearranging again like the first equation. This is equation number 2. And for side surface. And for side surface, there is no like uh, there is no surface resistance. So we can directly write EB3 is equal to J3, which is equal to sigma T3 raised to 4. So now our task is to find out what is J1, J2, and J3. So for that, we need to evaluate, or we need to solve this set of equations. So I'm not solving this right now. So this EB1 we know, that is sigma T1 raised to 4. This T1 is already given, and EB2 is also, we know, that is the temperature is also given. Then this emissivity is sigma 1 is given, sigma 2 is given, and also F21 we already found out, that is F21 we already found out in this previous question, that is 0.38, that is F12 0.38 we already found out, and F13 is we all F13 also we found out, that is 0.62, and here F21 also we found out the previous question how much, 0.38, and F23 also we calculated, where we calculated F23. This one, 0.6. So just substitute these values and we'll get equations. So J3 we already calculated. So we'll get two equations in terms of J1 and J2, and you can solve by the equation. It's a set of linear equations where we solve a two set of equations. Like that, you can solve and you will get the, I'm just writing the final answer of J1 is equal to 11418 watts per meter square, and J2 is equal to 4562 watts per meter square, and J3 is 1452 watts per meter square. So the answer we want for this question is J1. So which is 11418 watts per meter square. So after this question is really simple. It's just till we need to first we need to draw the network and calculate for the each surfaces, that is right equation for each surface, and just solving the equations. Just we will get now we get the values of EB1, J1, J2, EB2, and EB3. Okay. So the next question is also a continuation for the previous question. That is, we have to determine the value of net rate of radiation heat exchange of the surface 3. So we need to find out the radiation heat exchange for the surface 3. So for that, we need the values of the previous question, that is J1, J2, and all is near. So here, this is Q1, Q2, okay. So Q1 is equal to EB1 minus J1 divided by 1 minus epsilon 1 by epsilon 1 A1. So now we know epsilon 1, so sorry, EB1. So EB1 is equal to 5.67 into 10 raised to minus 8 into what is the temperature? 700 K. 700 raised to 4 minus J1 we already calculated 11418, all divided by 1 minus epsilon 1 is 0.8. 0.8 divided by 0.8 into the area 1. So area of 1 is what is the diameter? Radius and diameter is 1. Radius and height is 1. So pi r square, that is pi into 1 square. So this, if you calculate, you will get the answer as 27.6 kilowatts. Like that also, if you calculate Q2, that is EB2 minus J2 divided by 1 minus epsilon 2 to epsilon 2 A2, we will get 5.67 into 10 raised to minus 8 into the second surface is at 500 Kelvin. 500 raised to 4 minus J2 is given 4562, whole divided by 1 minus epsilon 2 is how much? 0.4. 0.4 divided by 0.4 into pi r square, 1 square. So this you will get it as minus 2.13 Kelvin. So if you see the So if you see directly, you can write what is Q3, because whatever, so what that is emitted from this uh, first body, it is equally, means it is part of it is falling on the 3, and part of it is falling on the 2. So it's like so whatever heat that is transferred, that is the net heat transfer from the surface 1. Some part will be going to part 3 and some part will be going to part 2. So we know Q1 is equal to Q2 Q2 plus Q3. Okay. Q dot 2 plus Q dot 3. So Q dot 3 is equal to Q dot 1 minus Q dot 2, that is So I'm netting and taking the absolute values only. So Q1 is we got how much 27. So 27.6 minus 2.13, which is equal to 25.5 kilowatt. So this will be the, so this negative. So negative minus 25.25, which means that the surface is receiving heat, right? Means the part of the heat that is ejected by the surface A, some part is going to 3 and some part is going to 2. Okay. So in order to maintain this steady state, means this temperature, so we have to continuously supply this 27.6 kilowatt of heat to the top surface 1, and we have to continuously take off the heat of minus of 2.13 from the bottom surface and 25.5 kilowatts from the side surface. We have to take this amount of heat and we have to supply 27.6 kilowatt of heat to the top surface in order to maintain the system at steady state, or in order to maintain these temperatures that it is given, that is 700, 500 and 400. Okay. So let's move on to the last question, which is also a question related to the uh, propellant. Sorry, the it's a question related to the radiation shield. So we have a cylindrical, we have the end of a cylindrical liquid cryogenic propellant, uh, which is used to, in free space, is used to be protected from external radiation by placing a thin metallic sheet in front of the tank. Assume B factor between sheet and the tank is unity. All the surfaces are diffuse and gray, and the surroundings are at 0 Kelvin, sorry, not degree, 0 Kelvin. Find the temperature of the shield and the heat flux at the end of the tank. Okay, so these options are not of this. So we have a tank, and there is some radiation that is coming into the tank. So this is filled with a cryogenic liquid. We have, and a shield is there to protect it from the, to protect the heat gain of the, or to reduce the heat gain of the liquid propellant. And we have to find out what is the temperature of the shield. So let's draw the shield here. So this is the shield. So if you consider this shield alone, some part of energy is coming, that is alpha SG GS. That is alpha S is the what? Is the absorptivity of the shield. Some part of the radiation is coming and some part is ejected. That is E. That is E shield. That is sigma EBTS, and the net heat flux that is going to the this tank is QS. We will regard it as QS. So by energy balance, this should be equal to okay. So this is the difference of whatever coming in and whatever going out. That is the net heat flux of this shield. So that is the, this is the net heat exchange between shield and tank. Okay. So So next, first question, we have to find out what is the temperature of the shield. So we are considering these this shield and the this tank surface 3T as two parallel surfaces. So we can write the equation, that is sigma times this is these two surfaces, this end of this tank and this shield as two parallel sheets. So we can write the net radiative heat, the heat exchange between two parallel plates, that is that surface, that equation, that is Tt4 1 by epsilon S plus 1 by epsilon. So this side, right? Epsilon 2 plus epsilon T minus 1. So epsilon T and epsilon 2 also given. And we need to find out, from this we need to find out what is Ts. But for finding Ts, we need to find out what is the net heat, radiative heat exchange. So for that, we just equate alpha S Gs minus epsilon epsilon 1 EB, or we can write that as in temperature of the shield. As the steel, it is already mentioned that the surfaces are diffuse and gray. We can write alpha S by Kirchhoff's law. Alpha S is equal to epsilon 1. So if you substitute these values, so epsilon 1 Gs already given, minus so all means except Ts, all the values we know. So if you substitute this, you will get the value of Ts as 338 Kelvin. So because epsilon 1 is given, Gs is given, then epsilon 2, epsilon 1, every values are given X. So from this we can find out what is Ts. So by solving this equation. So first question we got, that is the temperature of the shield and the net heat flux. That is, we can substitute this in this value in this equation. This is epsilon T. So if you substitute this in this equation, you will get the answer as 25.3 watts per meter square. So now it's just a substitution of the values only after this point. Okay. So here comes the end of our session. So actually, we took, this was a 12-week course, and we also took 12 live sessions. So in these sessions, I tried to solve some questions that are related to the topics that were covered in the previous weeks. So I hope this session was useful to you, and you have learned something new, and also you got some practice questions for the examination, and also this session helped you in solving the assignment part of this online course also. So all the best for the your exam, online examination, and all the best for your future. Okay, thanks for joining, and thank you, thank you everyone.